Hello, my dear students. Welcome to the session. Continuation of important observations from power electronics concepts. In this session, with respect to module 2 rectifiers, that is AC to DC converters, I would like to discuss about concept of single phase semi converter, that is off control rectifier. All of you concentrate. Students, we know that a semi converter is also called off control rectifier. The off control rectifier is a combination of thyristors and diodes. But point you have to remember, half wave is different, half controlled is different. Half wave is only one device, but half controlled is combination of thyristors and diodes. In semi converter, again there exist two types of configurations. One is a symmetrical semi converter, another one is asymmetrical semi converter. But point to remember, students, simply they given semi converter, you have to take the symmetrical semi converter only. If they given asymmetrical semi converter, then only you can take asymmetrical semi converter. Then what is the main difference between symmetrical semi converter and asymmetrical semi converter? In any converter, both controlled and uncontrolled devices. Which is the controlled device? Thyristor. Which is the uncontrolled device? Diode. If both controlled and uncontrolled devices conducting with the same angle, then it is called symmetrical converter. These observations mainly we have to observe in the inductive loads only. We can't see this observation in resistive loads. The conduction angles difference, that is in symmetrical semi-converter and asymmetrical semi-converter, the conduction angles differences are we have to see only in inductive loads. But for resistive loads, the conduction angles of symmetrical semi-converter, the conduction angles of asymmetrical semi-converters are same. But only in inductive loads, the conduction angles of symmetrical semi-converter, the conduction angles of asymmetrical semi-converter is different. In any converter, if both controlled and uncontrolled devices conduct with different angles, then it is called asymmetrical semi-converter. In symmetrical semi-converter, controlled device and uncontrolled devices are conducting with same angles. But in asymmetrical semi-converter, controlled and uncontrolled devices conducting with different angles. That observations we have to see mainly in the inductive loads. This is the first configuration of semi-converter, that is a single phase semi-converter using resistive load. This is the symmetrical semi-converter, this is the asymmetrical semi-converter. Just by seeing the configuration, we have to identify which is the symmetrical, which is the asymmetrical strength. In symmetrical semi-converter, one leg consists of thyristor diode, thyristor diode. That is, each leg consists of thyristor and diode combination. But in asymmetrical semi-converter, one leg is completely thyristor, one leg is completely diode. Then it is asymmetrical semi-converter. Then for resistive loads, this is the operation. But no need to concentrate on operation. For quick reference point of view, mainly you have to concentrate only the analysis points. So many times I given this statement. With respect to rectifiers, even in power electronics, formulas are very important. If you see the previous questions with respect to power electronics subject, mainly in GATE exam, most of the questions are direct formula based questions only. That's why my suggestion is mainly you have to concentrate on analysis points and you have to practice whatever the questions that I given. That preparation is enough. But in operation point of view, mainly concentrate on the conduction angles. It may be symmetrical semi-converter or asymmetrical semi-converter. Each SCR conduction angle is pi minus alpha. Each SCR conduction angle is pi minus alpha. Even each diode conduction angle also pi minus alpha for resistive load swing. These are the waveforms. In semi-converter also, for one cycle, how many pulses we are getting? For one cycle, we are getting the two pulses. That's why it is a two pulse converter. Once it is a two pulse converter, what is the ripple frequency? 2f. Even full wave rectifier is also two pulse converter. Semi converter also two pulse converter. But main difference is in full wave rectifier all the devices are thyristors. But in semi converters, combination of thyristors and diodes. And this is the thyristor current and diode current waveform, T1 D1 waveform, and this is the source current waveform. For resistive load, source current is the sine wave. Mainly you have to concentrate on analysis. To remember for resistive loads, to remember the formula for resistive load, Single statement is enough. Semi-converter with R load, the formulas are similar to full wave rectifier with R load. That is, whatever the formulas we are studied in full wave rectifier with resistive load, the same formulas are applicable for semi-converter with resistive load also. It may be symmetrical converter or asymmetrical converter. With respect to resistive load, there is no any difference. Even conduction angles also no difference in symmetrical and asymmetrical. That is, peak inverse voltage is Vm. Similar to full, this statement I given. For R load, the waveforms and analysis of single phase semi-converter similar to single phase full wave rectifier using R load. Peak inverse voltage Vm, circuit turn off time pi by omega, each SCR conduction angle is pi minus alpha, each diode conduction angle is pi minus alpha. These formulas are applicable for both symmetrical and asymmetrical. In resistive load, there is no any difference. In inductive loads only, some formulas are different in symmetrical and asymmetrical. Which formulas are different, that you have to see in inductive loads. Average output voltage, friends, Vm by pi into 1 plus cos alpha, important. In semi-converter for any load, mainly for R load and RL load, RLE load, the output voltage formula is same. That is Vm by pi into 1 plus cos alpha. Then what is the RMS output voltage? Similar to full wave rectifier with R load. That is Vm by root 2 pi into, that is pi minus alpha plus 1 by 2 sin 2 alpha whole to the power of 1 by 2. Then this is the RMS output current. This output power formula. And you have to remember output power. V naught equal to V naught RMS square by R. This is input power factor formula. V naught RMS by Vs. What the average value of each thyristor current, that is equal to each diode current also, both are same. Because along with the thyristor, diodes are conducting. This is the RMS value of each thyristor current. During operation, if any one SCR is damaged and open circuited, it acts as a half wave rectifier. In a half wave rectifier, what is the V naught? Vm by 2 pi into 1 plus cos alpha. In semi-converter also, during the operation, if any one thyristor is damaged and open circuited, the output is half wave rectifier output. In a half wave rectifier, what is the V naught, friends? Vm by 2 pi into 1 plus cos alpha. This problem you have to practice. Just practice the analysis, whatever I given, and you have to practice this model of questions. That preparation is enough for semi-converter with resistive load. Here firing angle it is asking, just average output voltage is given, then firing angle equal to 120 degrees. In the above problem, if the firing angle is 90 degrees, calculate the RMS output voltage. This is the RMS output voltage. If they ask the what is the power output power, then you have to do V naught RMS square by R square. Just remember the configuration. This is the configuration of single phase semi converter using R load. This is for symmetrical and this is for asymmetrical. But resistive load point of view, symmetrical and asymmetrical, there is no any differences in the formulas. For both symmetrical and asymmetrical, the formulas are same. Minimum try to remember average output voltage formula. This is important. And RMS output voltage formula and output power formula. These three formulas are very important with respect to resistive load. Next, one more configuration of single phase semi converter, that is using RE load, that you have to concentrate. Then this is the single phase symmetrical semi converter using RE load. This is the single phase asymmetrical semi converter. How to identify? Using the configuration. One leg is completely thyristor, one leg is completely diodes, asymmetrical. Each leg is combination of thyristor diode, then it is a symmetrical. Simply they given semi-converter, friends. But in the exam, in framing of any question, they are not given symmetrical or asymmetrical. Simply they given semi-converter. Semi-converter means you take symmetrical only. If they given asymmetrical, then only you take asymmetrical semi-converter. This is the operation. In operation point of view, no need to remember. No need to analyze in detail. Just you have to remember the conduction angles. And we know that in RE load case, minimum angle at which thyristor is triggered, that is theta 1 equals sin inverse E by Vm. And you also remember the circuit turn off time. Directly you have to concentrate. No need to practice these waveforms. Directly you have to concentrate on the analysis. This analysis is very important. What is the peak inverse voltage? It's a Vm only. Then circuit turn off time is pi plus 2 theta 1 by omega. Circuit turn off time is pi plus 2 theta 1 by omega. Each SCR conduction angle is theta 2 minus alpha. Then what is the average load current? This is similar to full wave rectifier with RE load. Simply remember like this. Using R load similar to full wave rectifier using R load. Semi converter using RE load also similar to single phase full wave rectifier using RE load. Once you are remember the full wave rectifier R load formulas and RE load formulas, same formulas are applicable for semi converter also. But only for inductive loads only formulas are different for full wave rectifier and semi converter. The average load voltage is V naught equal to E plus I naught into R. Directly we have to apply this formula to find the average load current. Then what is the RMS output current? No need to practice RMS output current formula. This is the power delivered to battery. This is the power dissipated by the resistor. This is the total output power, and this is the input power factor. Here also during the operation, if any one thyristor damaged and open circuited, then the current is reduced by 1 by 2 times. This mainly you have to concentrate on analysis point of view. After practicing that analysis points, better to practice these problems. Whatever the model that I solved, that practice is enough. Once again, I am repeating the same statement. Just practice the formulas and solve this model of question. Here it is asking that calculate the average load current and voltage. Directly apply the average load current formula. This I naught equal to 2 Vm by pi r. Sin of alpha plus gamma by 2 sin gamma by 2 minus E gamma by pi r. Once you know the average load current, then you have to calculate average load voltage, students. The average output voltage V naught equal to E plus I naught into R. This is about the semi converter using RE load. The next one is a single phase semi converter using RL load and RLE load. But point you have to remember, students, it may be RL load or RLE load. Same formulas, same analysis, same waveforms. Only difference is I naught formula. If it is RL load, you have to write I naught equal to V naught by R. In full wave rectifier also I given this statement. Na? In RLE load, then how to write I naught equal to this? You can write V naught minus E by R. Except this difference, remaining waveforms and analysis for both symmetrical and asymmetrical semi converter, RL load and RLE. I am telling that RL load and RLE load, there is no difference in the formulas. Only difference is I naught form. But with respect to inductive loads, there is some conduction angles difference in symmetrical and asymmetrical. What is that angle difference also that you will see. This is the operation for symmetrical semi converter that you have to concentrate. And this is that is during positive half cycle. This is during negative half cycle. No need to concentrate on the operation. This is asymmetrical semi converter operation during positive half cycle. How much angle the thyristor and diodes are conducting. During negative half cycle, this is asymmetrical semi converter operation, students. Finally, you have to concentrate on the analysis. Yes, in symmetrical semi converter, each SCR conduction angle is pi, and each diode conduction angle is also pi, students. But you see in asymmetrical semi converter, each SCR conduction angle is pi minus alpha. Each SCR conduction angle is pi minus alpha, but each diode conduction angle is pi plus alpha. This is the main difference. Very, very important that you have to concentrate on. In symmetrical semi converter, each thyristor conduction angle is how much? Pi. Each diode conduction angle also pi. That is both controlled and uncontrolled devices are conducting with the same angle now. That's why it is a symmetrical semi converter. But you see in asymmetrical semi converter, each SCR conduction angle is how much? Pi minus alpha. Each diode conduction angle is how much? Pi plus alpha. Is it same conduction angles? No. That is controlled and uncontrolled devices are conducting with different angles now. That's the reason why it is asymmetrical semi converter that you have to concentrate. Now these are the waveforms. No need to practice on the waveforms. And what is the source current waveform? Source current waveform is quasi square wave. In semi converter, we don't get the square wave. Always for inductive load, the source current waveform is the quasi square wave. That point you have to remember. And this is for symmetrical semi converter waveforms. This is the asymmetrical semi converter waveform. No need to practice. But analysis is very important. Just you see the differences in symmetrical and asymmetrical. Most of the formulas for asymmetrical and symmetrical is same, except conduction angles and circuit turn off times. In symmetrical semi converter, important. In symmetrical semi converter, circuit turn off time is pi minus alpha by omega. But here asymmetrical semi converter circuit turn off time is pi by omega. Already In competitive exam based on this question is there, students. Very important. But here peak inverse voltage Vm. Here also same. Average output voltage is Vm by pi into 1 plus cos alpha. Here also same formula. That is V naught equal to Vm by pi into 1 plus cos alpha. The formulas which are different, that formulas only I am writing in asymmetrical. When I am not written these formulas means these are similar to this. That is the meaning. That point to remember. The RMS voltage of symmetrical and RMS voltage of asymmetrical is same. I naught RMS equal to I naught. Here also I naught RMS equal to I naught. Output power equal to V naught into I naught. Output power equal to V naught into I naught. Source current is quasi square wave. In asymmetrical also source current is quasi square wave. The average source current is 0. Here also average source current is 0. The RMS source current is I naught into square root pi minus alpha by pi. Here also RMS source current equal to I naught into square root pi minus alpha by pi. Each SCR conduction angle is pi, but here it is different. Each SCR conduction angle is pi minus alpha. Each diode conduction angle is pi, but here each diode conduction angle is pi plus alpha, students. Average value of each thyristor current equal to average value of diode current I naught by 2, but here I naught into pi minus alpha by 2. I naught into pi plus alpha by 2. Thyristor current, RMS thyristor current, RMS diode currents are equal, I naught by root 2. But RMS thyristor current and RMS diode currents are unequal. Then this is the input power factor. Input power factor formula is same. V naught into I naught by Vs into Is. Yeah, that points mainly you have to consider. This is the input power factor V naught into I naught by Vs into I naught. But here, what is the, here also input power factor is same na? V naught into I naught by Vs into Is. That is 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 not equal to I naught. RMS value of source current is not equal to average load current because of it is the combination of thyristor and diodes. This is the IS formula. What is this IS formula? This is the IS formula. Yeah, this mainly you have to concentrate. This one model of question that you have to practice. Simply remember, students, if the waveforms are asked for semi-converter, in semi-converter for any load, it may be resistive load or inductive load, we never get negative spikes. This is important. You see the waveforms. Even though it is an inductive load, are you getting any negative spikes here? We are not getting any negative spikes. This is important observation. It may be symmetrical semi-converter or asymmetrical semi-converter. We never get the negative spikes. Then we can easily identify if any question is asked based on the semi-converter waveforms. Then output DC voltage waveform it is asked. Here negative spikes, na, this is not the answer. Here also negative spike, this is not the answer. Both positive half cycle, negative half cycle is controlled. But here one half cycle only it is controlling, another half cycle it is not controlling. That's why it is not the answer. That is option B is the right answer. Like this you have to identify. And this problem you have to practice. Whatever the analysis formulas I given, based on that analysis formulas, we can expect this problem. You have to find what the average output voltage. This is the semi-converter. Two thyristors, two diodes. It is a semi-converter. If it is asked what is the average load current, I naught equal to V naught by R. What is the RMS output current? It is a continuous mode. RMS output current equal to average load current. What is the output power what is the output power, students? V naught into I naught. Average source current is 0. What is the RMS source current? I naught into square root pi minus alpha by pi. Input power factor. Average thyristor current. RMS thyristor current. Because it is symmetrical semi-converter. Symmetrical semi-converter, students. Just we have to practice this problem for semi-converter. Maximum we can expect the questions based on symmetrical. In asymmetrical semi-converter, the formulas which are different, that formulas only have to concentrate. Most of the formulas are same. There is no change in average voltage and RMS voltage. Only conduction angles are different. Circuit turn off time is different. One more configuration of semi-converter is RL and freewheeling diode and RLE and freewheeling diode, friends. It may be RL and freewheeling diode or RLE and freewheeling diode. Waveforms analysis all are same. Only I naught formula is different. I naught equal to V naught by R in RL and freewheeling diode. If it is RLE and freewheeling diode, what is I naught, friends? V naught minus E by R. That is the only difference. You see what is the operation of this circuit? No need to concentrate on the operation. Finally, you have to concentrate on the what are the analysis points. Even with freewheeling diode also, we don't get any negative spikes here. In R load also no negative spikes. RL load also no negative spikes. RL with freewheeling diode also no negative spikes. Always source current is quasi square waveform. And output voltage waveform is same for any load. For any load, output voltage waveform is same. That's why in semi-converter, average and RMS values for any load except RE load case, Remaining all the loads average and RMS values formulas are equal. Only conduction angles are different. This analysis mainly how to concentrate. With freewheeling diode, same that of R load except current waveform analysis. In every rectifier, I am giving this statement, friends. With freewheeling diode, the analysis is similar to resistive load. Only difference is conduction angles. That is current waveform analysis. Peak inverse voltage Vm, but here circuit turn off time is pi minus alpha by omega with freewheeling diode. Important. Each SCR conduction angle is pi minus alpha. Each diode conduction angle also pi minus alpha because it is a symmetrical converter. Freewheeling diode conduction angle, students, 2 alpha. In full wave rectifier also with freewheeling diode case, what is the freewheeling diode conduction angle? 2 alpha. What is the average output voltage? Same formula, Vm by pi into 1 plus cos alpha. What is the RMS output voltage, friends? Vm by root 2 pi into pi minus alpha plus 1 by 2 sin 2 alpha whole to the power of 1 by 2. This is the RMS current equal to average load current because the continuous mode. Wherever the continuous mode is there, RMS current, average currents are equal. This is output power V0 into I0 students. Source current waveform is quasi square wave. Then average source current is 0. For a quasi square wave, this is the formula for RMS source current. For a quasi square wave, this is the formula for RMS source current and input power factor. What is the average value of thyristor current? If you want to calculate average thyristor current, amplitude into how much angle each SCR is conducting, pi minus alpha by 2 pi. RMS thyristor current, amplitude into, if it is RMS, take the square root. Each SCR conduction angle is pi minus alpha. If the question is asked for freewheeling diode conduction angle you take 2 alpha by 2 pi. Then if it is RMS, you take square root. Easy to write. In discontinuous mode, this is the operation for continuous mode. In discontinuous mode, for beta greater than pi, students, SCR conduction angle and diode conduction angles, this is equal to pi minus alpha. But freewheeling diode conduction angle is beta minus pi. Important. This is for discontinuous mode. Discontinuous mode, beta less than pi. I told so many times. In discontinuous mode, beta less than pi. Even though freewheeling diode is present, freewheeling diode will not conduct. Then each SCR conduction angle is how much? Beta minus alpha. That you have to concentrate. This is RLE and freewheeling diode. Beta greater than pi. What is the conduction angles? RLE and freewheeling diode. And the average output voltage is this one, students. With the freewheeling diode case, RL and freewheeling diode, this is the average output voltage that you have to concentrate. That is for discontinuous mode. In full converter, if freewheeling diode is connected, it eliminates the negative spikes. It behaves like a semi-converter. In full converter, if you connect the freewheeling diode, then the freewheeling diode will eliminate the negative spikes. That output is similar to semi-converter. In semi-converter, if freewheeling diode is connected, it does not affect the waveform. We know that in semi-converter, we never get negative spikes, sir. If there is no negative spikes, then how it can eliminate the negative spikes? How freewheeling diode eliminates the negative spikes? That's why in semi-converter, freewheeling diode will not affect the waveform. But what is the reason we are connecting freewheeling diode? We have the doubt, sir. In semi-converter, there is no negative spikes. Why you are connecting freewheeling diode? The purpose of using freewheeling diode, important statement. The purpose of using freewheeling diode in semi-converter is for successful commutation at higher value of firing angle. For successful commutation of thyristors at higher values of firing angles, we are connecting the freewheeling diode in the case of semi-converters. In semi-converter, with the freewheeling diode, V0 is Vm by pi into 1 plus cos alpha. Without freewheeling diode also same because it cannot affect the waveform. But in fully controlled rectifier, with the freewheeling diode, Vm by pi into 1 plus cos alpha, students. But without freewheeling diode, 2 Vm by pi cos alpha. That is output voltage is changing. That is in full wave rectifier with freewheeling diode, without freewheeling diode, values are changing, average voltage. But in semi-converter, with freewheeling diode, without freewheeling, there is no change in the output voltage waveform because there is no negative spikes here. Then with freewheeling diode case, this value. Without freewheeling diode case, this case. Then always average output voltage in full wave rectifier, average output voltage with freewheeling diode, friends, always greater than average output voltage without freewheeling diode. The reason, in without freewheeling diode case, there is a negative spikes. Because of that negative spikes, the average voltage is reducing. And this problem you have to practice with respect to semi-converter. Here it is asking that what the average load current. What the RLE load with freewheeling diode na? Average load current equal to I0 equal to V0 minus E by R. First we have to find the average output voltage. Substitute the firing angle strengths. Then you can get average output voltage. Once you know the average output voltage, then you have to find the average output current. This is the one concept of a semi-converter, that is with freewheeling diode. And this problem also you have to practice. Whatever the formulas that I given, use that formula, solve this all these models of question. This is the expected model of question students. From this, any question we can expect in GATE exam. That's the reason why by covering all the models of questions that I solve this model. Just practice the formulas and you have to practice this question. And you have to practice this model of questions. Still, if you don't have any time, better to practice only questions, whatever I am giving. I am giving the guarantee. Surely we can expect from these models. But not the same values. These values may be different. Model is same. Next. One more important concept of semi-converter is input harmonic analysis of single phase semi-converter switch. That you have to concentrate. Input harmonic analysis of single phase semi-converter. With respect to input harmonic analysis of single phase semi-converter, we know that in semi-converter, the source current is quasi-square wave. A quasi-square wave is a non-sinusoidal waveform. Any non-sinusoidal waveforms are analyzed by applying the Fourier series. Then if you apply Fourier series for that waveform using this instantaneous current expression, then you have to find the A0 value, A0 zero space. An equal to minus I0 minus 2 I0 by n pi into sin n alpha. This An is defined only for odd values. For all the even values it is 0. Bn value is 2 I0 by n pi into 1 plus cos n alpha. This Bn is defined only for odd values. For even values it is 0. An, Bn values also very important for GATE exam. Once you know the A0, An and Bn values, substitute this A0, An and Bn values in this equation. Then we can get the instantaneous source current expression of single phase semi-converter. This is the instantaneous source current expression. From this instantaneous source current expression, you have to write the so many formulas in semi-converter. Those are the input performance parameters of a semi-converter. And this is a Fourier analysis of single phase semi-converter. Then if you apply the Fourier analysis, this is the summary. Instantaneous source current expression, this one. What is the displacement angle? Alpha by 2 students. What is the nth order harmonic displacement factor? Cos n alpha by 2. But the fundamental displacement factor is cos alpha by 2. See the difference. In full wave rectifier, what is the displacement factor? Cos alpha. But here displacement factor equal to cos alpha by 2. This is the 5-star formula. Then what is the maximum value of nth harmonic source current? This is the maximum value of nth harmonic source current. Then what is the RMS value of nth harmonic source current? This is the RMS value of nth harmonic source current. But mainly fundamental formulas are important. Fundamental means replace n equal to 1. What is the RMS value of, that is a fundamental source current? RMS value of fundamental, not nth harmonic. This is the fundamental harmonic current. The fundamental harmonic current equal to 2 root 2 by pi into I0 into cos alpha by 2. That is equal to 0.9 I0. This is 0.9 I0 into cos alpha by 2. Very important. But in full wave rectifier, it is 0.9 I0. But here extra we are getting cos alpha by 2. Just for full wave rectifier formulas, multiply with cos alpha by 2. That is the formulas of semi-converter. Easily remember like that. What is the RMS value of source current, students? In the case of full wave rectifier, RMS source current is I0. But here I0 into square root pi minus alpha by pi, students. Next, what is the current distortion factor? Current distortion factor equal to 2 root 2 cos alpha by 2 by square root pi into pi minus alpha. This square root is total. For total, this is the square root, students. That you have to concentrate. That is square root pi into pi minus alpha. Clearly I am writing here 2 root 2 cos alpha by 2 by square root pi into pi minus alpha. This is the current distortion factor of semi-converter. For the total harmonic distortion, the total harmonic distortion of semi-converter is pi into pi minus alpha by 8 cos square alpha by 2 minus 1 whole to the power of 1 by 2. What is the input power factor? This is 5-star formula. 2 root 2 cos square alpha by 2 by square root pi into pi minus alpha, students. We may expect the problem from this one. What is the input power factor? Very important is input power factor formula is important, and displacement factor, fundamental displacement factor. These two formulas are very important. Even for full wave rectifier also, that two models are very important. Next, what is the active power input? Active power input is V naught into I naught. What is the reactive power input? V naught I naught tan alpha by 2. But in full wave rectifier only tan alpha. But here tan alpha by 2. What is the apparent power, students? Square root active power square plus reactive power square. This one model of question that you have to practice. Single phase semi convert, that is half control rectifier with supply voltage 230 volts 50 Hz delivering power to a load of R equal to 10 ohms, L equal to 10 millihenry, E equal to 50 volts at firing angle alpha equal to 90 degrees. Then calculate V naught value. What is the I naught value? Then all the formulas you know. The RMS load current equal to I naught. The RMS source current. IS is the RMS source current, students. I naught into square root pi minus alpha by pi. Firing angle is 90 degrees. That you have to calculate. What is the fundamental source current? 2 root 2 by pi into I naught into cos alpha by 2. That is 0.9 I naught into cos alpha by 2. You have to calculate fundamental source current 3.404 amperes. Distortion factor cos alpha by 2, students. Alpha is 90 degrees, that you have to substitute. What is the input power factor? Very important, that I told. Distortion factor is important. In this, distortion factor is important. Even fundamental source current is also important. RMS source current is also important. Every model is important. Please practice this model of question. What is the current distortion factor? 2 root 2 cos alpha by 2 square root pi into pi minus alpha, students. This is the input power factor formula. Then what is the active power input? V naught into I naught. What is the reactive power input? V naught I naught tan alpha by 2. This model of question is important. And final observation, if you take with respect to full wave rectifier and semi converter, in single phase full wave rectifier input power factor is 0.9 cos alpha, students. But here input power factor is 2 root 2 cos square alpha by 2 by square root pi into pi minus alpha. Direct formula also we can expect. In full wave rectifier, the distortion factor equal to cos alpha, students. But in this, distortion factor equal to cos alpha by 2. In full wave rectifier, active power is V naught I naught, semi converter also V naught I naught. Reactive power input is V naught I naught tan alpha. But here V naught I naught tan alpha by 2. That is, at a given load and supply frequency for same firing angle, the reactive power input of semi converter is less than as compared to reactive power of the full wave rectifier. That is, semi converter draws the less reactive power. The input power factor of semi converter is greater than input power factor of full wave rectifier. That is, semi converter input power factor is more as compared to input power factor of full wave rectifier. Total harmonic distortion is less in the case of semi converter as compared to full wave rectifier. That's the reason why, in performance point of view, semi converter is better performance as compared to full wave rectifier. These formulas once again I written, that you have to concentrate. This is the proof only I given. This is the reactive power input V naught I naught tan alpha by 2. Once you know the reactive power input and active power input, tan alpha by 2 equal to Qi by Pi. That I told already. In full wave rectifier also tan alpha, but in semi converter tan alpha by 2. By giving reactive power and active power in semi converter, if they ask what is the firing angle, use this formula, friends. Use this formula. If current distortion factor is increases, total harmonic distortion is reduces. Then output voltage of semi converter is greater than full wave rectifier. Efficiency of semi converter is greater than full wave rectifier. Reactive power of semi converter is less. It draws the less reactive power as compared to full wave rectifier. Input power factor of semi converter is greater than as compared to full wave rectifier. Current distortion factor is also more in semi converter. Total harmonic distortion is less in semi converter. Then semi converter is better performance as compared to full wave rectifier. And this problem you have to practice. The given rectifier, the delay angle of the thyristor is measured 90 degrees and supply voltage it is given. You have to calculate what the input power factor. Input power factor is 2 root 2 cos square alpha by 2 by square root pi into pi minus alpha. Then substitute firing angle, then you can get the input power factor. If it is asked what the displacement factor equal to cos alpha by 2 squares. Very important that you have to concentrate. And one more question that you have to practice. What is the RMS value of fundamental source current? What is the active power input and reactive power input? Every formula you know. 99.99% students in power electronics, most of the questions in gate exam is direct formula based questions only. Direct formula based questions. Better to practice what are the models of questions that I am giving. Maximum this type of models only we can expect. This problem also you have to practice. And one more concept with respect to semiconductor, what the quadrant operation of semiconductors. What the quadrant operation of semiconductor. We know that in semiconductor, the average output voltage is equal to Vm by pi into 1 plus cos alpha. You substitute any firing angle between 0 to 180 degrees. What is the range of firing angle? 0 to 180 degrees. Now, for any firing angle in between 0 to 180 degrees, always V naught positive, I naught positive. That's why semi-converter is a single quadrant converter. In semi-converter, always V naught greater than 0, I naught greater than 0. Important. In semi-converter, voltage never be negative, current also never be negative. But in full wave rectifier, there is voltage may be negative. That is in fourth quadrant. Na? But here voltage never be negative, current never be negative. That's why always V naught positive, I naught positive. That's why semi-converter is a 2-pulse converter, single quadrant converter. But full wave rectifier is 2-pulse, 2-quadrant converter. But it is a single quadrant, that is first quadrant converter. V naught positive, I naught positive means power is positive. Then power is delivered from source to load. It is used only for motoring mode of control. That is, among all the converters, if it is asked only for motoring control, your answer is semi-converter. More preferable converter is semi-converter. For only motoring control, among all the converters, semi-converter is more preferable. For only motoring control, among all the converters, only semi-converter is more preferable. Then if you draw the control characteristics, in the case of full wave rectifier, both positive and negative values you got. But in the case of semi-conductor, always positive values. If you control the firing angle from 0 to 180, the output is controlled from 2 Vm by pi to 0. If you control the firing angle from 0 to 180 degrees, the output is controlled from 2 Vm by pi to 0 students. Why? Because the average output voltage is this one. In this substitute alpha 0 degrees, alpha 180 degrees. Then output is controlled from 2 Vm by pi to 0 volts. Okay, this is about the quadrant operation. Which quadrant convert this? Single quadrant, that is the first quadrant converter. I told already in single phase semi-converter, during the operation, if any one thyristor is damaged and open circuited, it acts as a only thyristor, then it acts as a not full wave rectifier, sir. Then it acts as a half wave rectifier. As a half wave rectifier. Among all the converters for only motoring control, semi-converter is more preferable. For only motoring control, semi-converter is more preferable. For example, for only motoring mode, if the question is asked, then what is your answer? Semi-converter. For both motoring and braking mode, full wave rectifier, semi-converter, half wave rectifier, none of the above. Your answer is full wave rectifier. For example, if the options are given like this, full wave rectifier, semi-converter, half wave rectifier, dual converter, then answer is dual converter. Important students. For both motoring and braking mode, if the question is asked, if the dual converter is not present, your answer is full wave rectifier. If the dual converter is present, don't select full wave rectifier, you have to select the dual converter for both motoring mode and braking mode. In the final session that I will give the what exactly dual converter also. But in this session mainly I am discussing only semi-converter students that you have to concentrate. And this is the special case of the semi-converter. Important note point that you have to concentrate. Very important students. This 2 times repeated in gate exam. If one thyristor and 3 diodes are given, then this thyristor conduction angle is pi minus alpha. Diode conduction angle is pi. D1 angle. D1 how much angle conducts pi. D2 how much angle it will conduct pi. D3 how much angle it will conduct pi plus alpha. This is the output voltage waveform we can get. That is, if 3 diodes, 3 diodes, 1 thyristor. 3 diodes, 1 thyristor is given. This is the output voltage wave shape. 3 diodes, 1 thyristor is given, students. This is the output voltage wave shape. Only one half cycle it is control, another half cycle there is no control. One half cycle only it is control, another half cycle it is no control. And let us assume that it is a continuous mode of operation. But formulas are very important. These are the detailed waveforms that you have to concentrate. Conduction angle of each device also I given. Mainly, this is the source current waveform. Still now it is not asked source current waveform, but we can expect source current. But exactly is not a quasi-square waveform. This is positive half cycle. This is for negative half cycle. See the source current waveform for 3 diodes, 1 thyristor. But average output voltage formula. Based on the average output voltage formula, question is repeated in gate exam. If 3 diodes, 1 thyristor is given, it is also asymmetrical configuration. Then V naught equal to Vm by 2 pi into 3 plus cos alpha students. What is I naught equal V naught by R? This is the average thyristor current. This is the RMS thyristor current. Average D1 diode current. Because D1 diode is conducting pi angle na, that is I naught by 2. RMS D1 diode current I naught by root 2. D2 diode current students. D2 diode is also conducting pi angle na, pi by 2 I naught by 2. RMS value of D2 diode current I naught by root 2. D3 diode. D3 diode is conducting pi plus alpha na. Then this is the D3 diode RMS current. Source current. Source current is not pi minus alpha. This is 2 pi minus alpha by 2 pi. This is important. Concentrate. If 3 diodes, 1 thyristor is given, if it is asked what the RMS value of source current, the RMS source current equal to I naught into square root 2 pi minus alpha by 2 pi student. This is the output power expression. This is the input power factor expression. And output power equal to V naught into I naught. Input power factor equal to V naught into I naught by Vs into Is. This is the special case of the semi-converter if 1 thyristor and 3 diodes are given. Yes friends, with this, with respect to module 2 rectifiers, that is AC to DC converters, the detailed discussion of single phase semi converter, that is half control rectifier, is completed. This is about the session. Thank you.